Hello Physical Science, this is Mr. B. We're starting a new chapter today in our physics unit, that is chapter 12, and it is entitled Forces and Motion. So, gonna build on a little bit more of our last chapter. Remember, chapter 11 was just motion, and now we're gonna add something that are called forces. So, hopefully you've heard of what a force is. Maybe you can even make a little bit of an educated guess, but I would definitely make sure, just for the sake of the quiz tomorrow, make sure you're paying attention. Write down the title of this chapter, because that will in fact be the first question on the quiz tomorrow, is what the title of the chapter is. So we're going to go ahead and dive in for the first section, the new part of this chapter title, which is forces. So this first section is going to focus strictly on the forces portion, because again, that's something that we haven't gone over yet. So to start, we always kind of have our real life example here. So the first one being, it says the wind pushes against a man in his umbrella. The push from the wind is what we call a force. So that force in this case is the wind, and to give us an official definition to help us understand why the wind is considered a force, we'll just go to our next slide. And a force is defined as a push or pull that acts on an object. So the wind, and depending what direction it's coming from, it is pushing on the man's umbrella, so that is why it is considered to be a force. So a force is any push or pull that acts on an object, and as a result, a force can do a couple things. It can cause a resting object to move. That's one effect that a force can have. Or it can cause acceleration of a moving object by having the object change speed or direction. And if you remember, we talked about last chapter what acceleration is, how it can be the changing of speed or the changing of direction. So that's why a force can affect acceleration by altering any of those two things. And then just our next one's going to give an actual more real life example too, about how you've actually probably measured in your force in your lifetime. I know if you're like me, you probably played with these scales a lot when you were kids. These are called a spring scale. So you've measured force when you use a spring scale. So the stretch of the spring in the scale depends on the amount of weight. So weight is a new word that we're going to get an actual definition for, which is a type of force acting on it. So using these little scales right here, you are actually measuring force because, again, the spring will stretch depending on the type of force that you put on it. And we can also draw arrows that could represent a force. So the lengths of arrows show the relative amounts of force. So we can see right here, on letter A, we have a shorter arrow than in letter B, because if you look, we have more apples in letter B, so therefore a greater force is being exerted, and if you look there up on the scales, you can see why. So force is just any push or pull on an object. Again, an example that we've all seen in our lifetime is the spring scales that you see at grocery stores. And so now, to kind of maybe dive a little bit more into it, we're going to actually look at our units of force. So how we actually measure force is what is called a Newton. So I definitely make sure I write that down. So a Newton is a force, and if we get really specific here, that causes a 1 kilogram mass to accelerate at a rate of 1 meter per second each second. So our label for force is either going to be newtons or kilograms per meters per second squared. So that sounds a little bit confusing, but we measure force and basically how much it actually takes to move a 1 kilogram mass. So this is like our baseline. The 1 kilogram mass is our baseline, and our Newton is measured on how long it takes to accelerate that at 1 meter per second each second. So that'll make more sense as we go on when we actually work with some problems in determining force. When we see the labels that are associated with each thing, that'll make a Newton make a little bit more sense. But for now, know that is our SI unit for force is a Newton. So that is what scientists across the world use to calculate what force is. And so just to keep moving on, getting more specific about forces, again, we have a couple key questions here. It says, how do forces affect the motion of an object? So motion is what we spent our whole last chapter on. So now we're going to kind of look at how forces kind of play a role with how things can move. So when the forces on an object are balanced, the net force is 0, and there's going to be no change in the object's motion. So multiple forces can act on an object at one time. When that happens, there's going to be no change in the object's motion. However, when an unbalanced force acts on an object, the object's going to accelerate. And again, remember, that can be either speeding up or slowing down, because again, that one's deceleration, but they do both classify as accelerating. So hopefully, just from a logical standpoint, this makes sense. Balanced forces mean that equal things are acting upon an object. That means that an object is just not going to change motion because they cancel each other out. When an unbalanced force acts on an object, the object's going to accelerate because it's either going to increase speed or it's going to change its direction. And one term that was used in there that might be a little bit new to us that you probably need to know is the net force. So the net force is the overall force that's acting on an object after everything has been combined. So we can get net forces by adding forces that occur in the same direction, and then we can get a net force by when forces in opposite directions, they subtract from one another. So it's pretty much the same rule as velocities and things like that. Two velocities were moving in the same direction, we added them. When they were moving in opposite directions, we subtracted them. Determining a net force is the same way. If two things are pushing in on an object at the same thing, they're going to cancel out because they're coming in opposite directions. If two people push one boulder both on the same side, we're going to add the forces from both those people because they're both moving in the same direction. Two people are standing on opposite sides of the boulder and pushing in, then again, there's not going to be any net force because it's going to be in the same direction. They're going to cancel out. And then balanced forces are forces that combine to produce a net force of 0. An unlimited number of individual forces can act on an object to produce this. So one example that's a pretty good one, I think, of balanced forces is these two groups right here. They're pulling with equal forces in opposite direction, so therefore they're going to combine to make a net force of 0. So all of these people, again, this might not be a completely realistic situation, but based off of what's showing here, all these people are pulling with the exact same force at the exact same time. The center knot in the rope is not moving, so the net force is 0. So that is a balanced force right there, and we're going to do a little simulation in class where we take a look at balanced forces versus unbalanced forces, which is our next one. And this results when the net force acting on an object is not equal to 0. So for this picture, if we took away these two people in the back, instead of now having a balanced force, we're going to have an unbalanced force because the force coming in this direction is going to be much greater than the force going in the other direction. And just to wrap it up, again, kind of already alluded to this, but you can add or subtract forces. Again, if they're in the same direction, we add them. Opposite directions, we subtract them. And if they're equal and opposite, they're going to cancel each other out. They're going to be 0. So those forces follow the exact same rules of the velocity we use. Again, they're both kind of vectors here. We add them together, we subtract them, or they can cancel out altogether. So that is it for our first part of section 1. Let me know if you have any questions.